Before we begin, I want to kindly ask you a very small favor. I'll truly appreciate it if you could do at least one of these on the list. I am myself a physicist and I'll keep making more videos, always trying to give new stuff in them. Thank you. After 1850, the study of spectroscopy, or the light emitted from heated elements, developed rapidly. People back then thought that this light comes from vibrations. Hence, they looked after harmonic relations between spectral lights, but with no success. In 1885, Johann Balmer found that the wavelength of all spectral lines known back then can be calculated by the formula, where R is known as Rydberg constant. Balmer and Ritz then said that other hydrogen spectral lines exist if we generalized the term in the parentheses. And so the equation became for n bigger than m. Lyman found the ultraviolet series with m equals 1 and n equals 2, 3, 4, etc. Paschen discovered the infrared series with m equals 3 and n equals 4, 5, 6, etc. While Balmer's m was 2. Although these experimental equations were very useful, they had no theoretical explanation. In 1911, Ernest Rutherford suggested the nuclear atom. His experiments led him to the idea that an atom is a nucleus with a positive charge surrounded by negative electrons, where the electron was discovered by J. Thomson in 1897. However, classical physics didn't help Rutherford to give an explanation for the spectral lines emission based on his model. No stationary configuration of charges can be in stable equilibrium under their own electrostatic force, and so the electrons must orbit in some way, and the corresponding acceleration will result in energy loss by electromagnetic radiation. Hence, electrons will gradually spiral into the nucleus, and the atom will not exist. Moreover, the frequency of the radiation emitted will gradually increase as this spiraling continues, and a continuous spectrum will be produced instead of the observed discrete spectral lines. In 1913, Niels Bohr combined the nuclear atom of Rutherford with Planck's quantum hypothesis of 1900 to give a theory that accounted for the observed spectrum of hydrogen. Number 1, the electron is a particle revolves about the nucleus only in certain allowed orbits, which may be circular or elliptical. Number 2, each of these special orbits are stationary energy states in which electromagnetic radiation is not emitted. The allowed orbits are only those whose angular momentum is an integer multiple of the Planck's constant. Number 3, emission and absorption of radiation occurs when the electron makes quantum jumps from one of these stationary states to another. When it makes a transition from an orbit of a higher energy state E sub I to a lower energy state E sub F, then the energy difference is radiated as a photon of energy E sub I minus E sub F equals h times F, where the last F is the frequency. All of that is nice and good, only if the second point was physically justified. Bohr used classical concepts like the kinetic energy, Coulomb force, and the potential energy to calculate the energy of these stationary orbits or stationary states. The outline goes like this. This includes only circular orbits. Arnold Sommerfeld in 1916 generalized the Bohr theory to include elliptical orbits also. He said that the allowed states of a periodic system are determined by the quantum conditions, where p is the momentum and q is the same coordinate related to p. This is actually not all new. The angular momentum itself is given by p times r. The integration here is over a complete period of the motion. Now each coordinate will have its own n, and Bohr's n is the sum of these n's. What's also worth mentioning is that Bohr introduced the so-called correspondence principle. He argued that at high energy levels, the energy required to make a quantum transition from one stable state to another will be very small, and the quantum theory will give the same results as the classical theory. From Bohr energy formula, the transition photon will have the frequency. Now in the large n limit, this f will be very small, and so we can expand it in what's called Lorentz series. Only the first term is significant. The other ones are too small since the denominators became too big. Now in the classical theory itself, the frequency of the emission is equal to the frequency of the revolution of the electron in the circular orbit. So, if we substitute for the v and r from the equations we have already seen, then this classical frequency is equal to the quantum one. There is really this classical quantum correspondence for atomic high levels. However, after all, there were obvious weaknesses in the old quantum theory of Bohr and Sommerfeld. It was seen from the beginning to be a mixture of quantum and classical ideas. The electron was regarded as a point charge, whatever the system's dimensions might be. Also, the rules of Sommerfeld picked out the allowed orbits which had energies calculated using the classical theory. And the biggest issue was, after all, the assumption of Bohr that electrons only take specific orbits where they are stable and do not emit energy. This assumption is simply strange and had no physical basis. Now it's time for the particle-wave duality of the electron. As we have seen in videos 5 and 6 of this series, Louis de Broglie, using relativity of time and space, was convinced that any moving particle relative to some observer will have a wave manifestation of a wavelength lambda. What comes next was already known in classical physics, and this is what Bohr could have better done. The French mathematician Fermat established the principle of least time to light and optics. The time taken for light to trace from some point A to point B is given by the line integral, where v sub p is the phase velocity in the medium and is a function of position in general. Now, since the phase velocity of light can be written as where f is the constant frequency, Fermat principle becomes. Now in classical mechanics, the similar principle is the one of least action. For a single particle of constant total energy E and kinetic energy Ke, the Lagrangian is given by. Hence, we have, by changing the variable of integration from time to distance, it's not difficult to show that this final result can be written as. The similarity between Fermat principle and this mechanical equation is striking, which confirms further the idea of phase wave suggested by de Broglie and immediately gives the relation of de Broglie. I have already introduced this in video 5. Also, as in video 6, the atom is about 1 angstrom in size, and the wavelength of the electron of such energy as calculated by Bohr is also in order of 1 angstrom. Hence, the electron in the atom exhibits high wave properties. From the reasoning we just made, one can replace Bohr's particle electron with a wave. This de Broglie wave represents an electron, as we saw in video 5. And so, it must here also be spatially periodic in its place around the atom. And this is great because now the electron's orbit should satisfy some mechanical condition, that is, only those orbits whose length is an integer number of wavelengths are allowed to be occupied by the electron. De Broglie's wave solved the problem of the unjustified stable orbits of Bohr and made the atom a real stable quantum system that can only be studied using quantum wave mechanics. Remember the phase wave we saw in video 5, or go see it. Now we wrap it around the circumference of the atom. This is for n equals 1. The circumference is 1 wavelength long. This is n equals 2. equals 3, 4, 5, 6, and so on. Subscribe and stay tuned for the next video, where we'll establish the next developments of the quantum theory and explain the very probabilistic nature of matter on the quantum level.